I have drawn here a very basic, generic sort of velocity time graph. The graph shows the motion of some object that is already traveling at some initial velocity and then accelerates for a certain length of time to some final velocity. An example would be you're driving down the road in your car at 30 miles an hour and you accelerate to get on the freeway to 75 miles an hour, perhaps. So you would already have some velocity before you started. You didn't start from a dead stop, and by the time you're on the freeway, you need to be going freeway speeds. That takes a certain length of time. You're going to travel a certain amount of distance. You're going to have some certain acceleration based on the capabilities of your automobile. I wrote over here a couple of the basic big ideas that we need to always keep in mind. Okay, slope of a velocity graph is the acceleration of the object. The area is the displacement. So just to help visualize the area, I'm going to drop a line down here to the time axis. And that's kind of an unusual shape, but it looks to me like it's just a triangle stacked on top of a rectangle. Okay? So in order to find the area, I just need to find the area of the rectangle and the area of the triangle and add them together. Triangle plus rectangle. I'm going to be developing the 4 kinematics equations that we will see most frequently in class and use most often. The first, I'm going to start with writing an equation for slope. Okay, we know that slope equals rise over run. So let me just start with that. Slope equals rise over run. So that means that acceleration, we're going to use the symbol A for acceleration, delta x for displacement, t for time, v0 for starting velocity, v for final or ending velocity. The acceleration is equal to the rise divided by the run. Well, the graph goes from v0 up to v, this amount right here. Okay? And that amount can be found if we calculate, since v is a bigger number, I can calculate that amount of rise by taking the final velocity and subtracting the initial. You start at 30 miles an hour, you end at 75, your change in velocity is 45, 75 minus 30, 45. So, using just symbols, v minus v0, and the run of this graph, okay, I did rise divided by run, and the run is the amount of time it takes to cover that distance and experience that acceleration. We typically write this equation slightly differently. I'm going to multiply by t to get it out of the denominator. So I have a times t equals v minus v initial. And then finally, we usually add v initial to both sides and swap it around, so we end up with v equaling a times t plus v initial. This is the first of our kinematics equations, by the way. This is really just the equation of this line in slope-intercept form. It looks confusing because it's all symbols, but really it's just saying that the value here on the graph, okay, any value of v on the graph is equal to the slope times the x variable plus the intercept. Okay, so it's really just y equals mx plus b. I know it doesn't look like it, but that is exactly what it comes out to be. There's the first of our kinematics equations. Let's call that 1. Next, area equals displacement. So I have a rectangle. For the area of a rectangle, displacement will equal height, v0, times length, t. This is a useful equation if velocity is constant, but since velocity was not constant and changed, I also need to make sure I add in the triangle on top. So delta x, The area of a triangle is 1/2 the base, which is t again, times the height. And the height of this rectangle, this triangle, we've already seen is v minus v initial. So adding those two together, we get that delta x total is equal to v naught times time plus 1/2 times time and v minus v initial. We almost never write it that way. We can simplify this just a little bit by using the distributive law and getting v initial times time plus 1/2 t times v minus 1/2 t times v initial. Here I have a 1 v initial times time, and here I have a 1/2 v initial times time that I'm subtracting, and so the result of that is 1/2 of v initial times time plus 1/2 of v times time. And finally, we can use the distributive law again in reverse, and we normally end up writing this equation as 1/2 of v initial plus v times time. There's the second of our kinematics equations. The other kinematics equations are obtained by substituting different versions of those two equations together. The first one I can get by looking here and here. All right. I noticed I actually look over here to this one, so I'm going to take this version of the equation and notice v minus v naught, and I'm going to plug it in over in this equation. So that would give me, starting here at delta x again, delta x equals v0 times t plus 1/2 times t, and then in place of v minus v0, I have a times t. Because v minus v0 is the same thing as at, I can substitute. Now, simplifying just a little bit, delta x equals v naught t plus 1/2 a t squared. T times t is t squared. A doesn't do anything, the half doesn't do anything. There is the third of our kinematics equations. And the last one is obtained by substituting by solving for t and substituting. So I'm going to take this equation, solve it for t. So coming back over to here, I get that t would equal v minus v initial over a. And then taking that value for t and plugging it in right down here in equation number 2. So delta x equals 1/2 v plus v initial. I can switch addition that way. T, which would be v minus v initial over a. Now a little bit of algebra. I'm going to multiply both sides by 2 to get rid of my fraction. Multiply both sides by a to get rid of my fraction. That will give me 2 times a times delta x over here, and leave me with v plus v initial and v minus v initial. You ought to recall from your math class that this is one of those special sort of polynomials here, so that 2 times a times delta x equals v squared minus v initial squared. Just the pattern that forms. Again, we typically write this by adding v initial to both sides and then swapping the sides around, so v squared would equal v initial squared. After adding it to the other side, it's positive, plus 2 times a times delta x. And there is the fourth of our kinematics equations. We'll leave it there for just a second. To use them, we typically just write them all down. We have V equals V naught plus AT. There's one. 2 is delta X equals V naught T plus 1/2 AT squared. 3 is delta X equals V naught T plus, I wrote 3 first. This one's 3. This one's 2. I'm going to start this part over. Equation number 1. V equals V naught plus AT. Equation number 2. Delta X equals 1/2 V plus V naught times time. I'm just writing them out the way that they are normally written in most physics books. They're not necessarily numbered 1, 2, 3 in the same way, but they're written out in pretty much the same order. V naught T plus 1/2 AT squared. And finally, equation number 4, V squared equals V initial squared plus 2A delta X. Now our 5 variables are delta X for displacement, time, acceleration, V initial, and V final. So you can actually recognize which of these equations to use at any one moment by identifying the missing variable of these 5, which one is missing. This equation never uses delta X. If you were asked to solve a problem that you didn't need to know the distance or weren't told the distance, this would be the equation to use, number 1. This equation never uses acceleration. Doesn't mean acceleration is not happening, you just don't know the value, don't need to know the value. This equation never uses V final. Once again, doesn't mean it doesn't have some final speed at the end. It just means you don't know what that speed is, and you don't really need to know what that speed is. You're not looking for it. And finally, the 4th equation, T, is the missing variable at all times, and you don't know the time, you're not asked to find the time. Finding the time would be difficult, and so this is the equation that would not involve time. You wouldn't even be able to solve for time. There's actually a 5th equation that has V initial as the missing value. That equation is hardly ever used, and so we're not going to worry about it for our examples in class.